Hello everyone, welcome to my channel, Indian School of Physics. Guys, today I have come up with another amazing problem from Pathfinder. It is falling sand and rotating disk. Guys, this video is brought to you by Indian School of Physics and Unacademy together. And guys, my current courses on Unacademy are INPHO Foundation and JEE ADVANCE 2023. And another upcoming course on Advanced 2021, it will be Advanced Problem Solving course, starts next week. And guys, it will be a very amazing course. So those who are interested in looking for Advanced 2021 can access this course. And other than that, there is an advanced course on electrostatics for JEE 2022. It started on 17th February. And the upcoming course from 12th March, it is advanced course on electrostatics for JEE 2022. It will be in English for students of South. And guys, you can access my theory courses which are of advanced plus level for boosting your JEE preparation. It will make a lot of difference in your preparation, and you can unlock courses, test series, free lectures on Unacademy using my code Nitin sir. And for more information, you can visit www.unacademy.com. And guys, trust me, physics will never be the same again. So here is the statement of this problem. A disk of radius r inclined at an angle of theta with the horizontal is evenly covered with a thin layer of sand. The coefficient of friction between the sand and the disk is mu. The disk is made to rotate about its vertical axis of symmetry with gradually increasing angular velocity. The angular velocity is increased so gradually that the tangential acceleration of any of the sand particle is practically negligible. What is the angular velocity of the disk when eta fraction of the sand has fallen off the disk? Acceleration due to gravity is g. And a very valuable hint is also given in this problem, that is, sand particle at the lowest position has the maximum tendency to slide off the disk. So we will check, he is talking about this point. We will see how this point has the maximum tendency of falling off the disk. So guys, let's discuss the concept part here. Since acceleration due to gravity is vertically down, so in this case, along the surface of the disk, component of g sine theta will be present, and perpendicular to the plane of the disk, it will be g cos theta. So I'm just going to rotate this diagram slightly, so that because we are more comfortable in solving problem in this kind of diagram. So here now this vertical component is g cos theta, and along the surface it is g sine theta, which is towards the left part. So let's consider a particle which is present at some dm mass. It is the sand particle. Now if you see, there are two forces here. Due to gravity, its weight, you can say dmg sine theta and dmg cos theta, which is acting here. Now let's observe this particle from the rotating frame in the next diagram. If you try to observe this, so you will see with respect to rotating frame, apart from the weight components dmg sine theta and dmg cos theta, and the normal reaction is dn, and here the pseudo force or centrifugal force dmr omega square is also acting along with this. So you can see that the dmg sine theta and dmr square both are acting in a radially outward direction for this particular direction here, and that is what is providing the maximum pull. For a larger will be the arm and larger will be the pull in this case, because dmg sine theta is constant. So the particle will have tendency of, or you can say this particle has the maximum tendency of sliding off this plate or disk. So that's what was given in the hint, and you can understand because this centrifugal force will become the maximum at this particular point for a given omega. Now here I have written the particle which are on the lower side have greater tendency of falling off the rotating disk, as both gravity and centrifugal force relative to the disk are acting in the same direction. That will be the that will not be the case at any other point if you check, because then resultant force will decrease, and the friction will be acting towards the center, as here you can see the overall this particle, let's assume it is not sliding just now. Now for a given angular velocity omega, we can say the particle which is present at a distance of r, let's say it is about to slip. It is about to slip. right? So we can write here this dn is dmg cos theta, and similarly this friction force will be dmr omega square plus dmg sin theta. And for no slipping or no sliding, I can write this dfr as less than or equal to mu into dn. If I substitute the value of dn, I'm going to get this value of omega square, which is less than or equal to mu g cos theta minus g sin theta by r. That means if omega reaches this particular value for a given r, in that case it will be just about to slip, and definitely all the particles which are present at r greater than r will definitely slip whenever they will pass through the lowermost position. So you can see in this diagram, so all these particles which are lying in this blue region, that is small r to capital R, they will slide once they will pass through this position. Once they will pass through this lowermost point, here maximum pull force will be generated on the particle, and it will slide if friction is crossing the maximum limit of it, for which omega we have calculated. So from here I can say all the particles in the shaded blue part, as these particles will come to the lowermost point during the rotation, they will slide off the disk. That means here this particle is not sliding, all these particles are not sliding, but when they will come to this position during the when they will cross this line, at that time they are going to slip and they will slide off the disk. So you will find only in this gray part these sand particles will be left. And one more information is given here, that is the fraction. So I can say it will be the particle present in the area of blue part divided by total area of the disk, that is total sand particles, and its fraction I can relate with the area. So area of the blue part I can write as pi capital R square minus small r square divided by pi capital R square. So when I simplify, I am going to get this r value as small r is equal to capital R root of 1 minus eta. You can see here omega square was having this value. So if I substitute the value of r in this situation here, omega square, I am going to get mu g cos theta minus g sin theta, and that is equal to r times root of 1 minus eta. So when I substitute here, then I'll get the angular velocity for which eta fraction of the sand particles will slide off. So it will become root of mu g cos theta minus g sin theta by r times root of 1 minus eta. This is going to be the final answer for this problem. I hope guys you have enjoyed this solution. It was easy, slightly I'll say it was on the tougher side, this problem, because understanding this, that all the particles when they will cross this lowermost position are going to slide, not otherwise, not for a omega, that it will not be like this particle will slide in this situation. No, when they will cross through this lowermost point, they are going to slide. That was the tricky part of this problem. So I hope you have enjoyed it. If you have enjoyed it, please share this video with others and like it. If you haven't subscribed my channel, please subscribe it. I'll be coming up another video very soon. Thank you. Thanks for watching it.